So now let's look at growth rates of functions. When we talk about growth rates in this concept, it is not just saying which slope is steeper. So let me put that down. It is not just about the steeper slope. Okay? What's actually going on here is we are trying to group up functions in how they grow. So I'm not going to be saying that that 2x grows twice as fast as x. I'm going to be trying to show that x squared grows much faster than x. And here's how we do it. So 3 possibilities. So given 2 functions, f of x and g of x, if the limit as x approaches infinity of f of x over g of x equals infinity, then, and it's up 2-way, then f of x grows faster than g of x. Or I could also say g of x grows slower than f. If the limit as x approaches infinity of f of x over g of x equals 0, then f of x grows slower than g of x. Or I could also say that g of x grows faster than f of x. And finally, and I'm going to be only concerning myself with positive as I go out towards infinity, f and g. So I'm not going to consider negative infinity here. But if the limit as x approaches infinity of f of x over g of x is equal to some limit L, where L is a positive, non-zero real number. So it's between 0 and infinity. It's not infinity, it's not 0, it's somewhere between there. Then we'll say that f of x and g of x grow at the same rate. Now, the example, so I gave the example earlier of 2x and x. 2x divided by x is 2. So in some concept you might think, okay, 2x is twice as steep as x, but their growth rates, we're going to say, are the same because they're both lines. Let's see some examples. First example. Does f of x equal x to the 1000 or g of x equal e to the x grow faster? Well, I'll consider the limit as x approaches infinity of, and it doesn't matter which one I put on top. I'll put x to the 1000 on top. X to the 1000 over e to the x. And we saw earlier about L'Hopital's rule where as x is approaching infinity, the numerator and denominator are both approaching infinity. So that means I can take the derivative. But that doesn't seem to help very much because now I'm just going to get to 1000 x to the 999 over e to the x. And I can see that the numerator and denominator both approach infinity still. And if I took the derivative again, I get the limit as x approaches infinity of 1000 times 999 x to the 998 divided by e to the x. But if you consider what happens as I go further and further and further, so it's still going to infinity over infinity. If I take this derivative 1000 times, I make sure I'm doing that correctly in my head, actually 999 times, so I'll put a little ellipsis, I will get to the limit as x approaches infinity of 1000 factorial x over e to the x which still approaches infinity over infinity. But when I take this derivative, the important part is eventually this numerator is going to go to a constant, 1000 factorial. The denominator is still going to be e to the x because the derivative of e to the x is e to the x no matter how many times I take it. And when I have a constant, even an exceedingly large constant like 1000 factorial, divided by something going towards infinity, it equals 0. What that means that the bottom was growing bigger than the top, so g of x grows faster. Alright, second one. Now this one has a little trick to it. Does f of t equal 5t plus cosine t, or g of t equals 2t grow faster? And so I'll start the same way. Limit, as t approaches infinity, of 5t plus cosine t divided by 2t. And here's the problem. As t approaches infinity, I can see that both the numerator and the denominator approach infinity because this is going to go towards infinity. This will be bounded between -1 and 1. So I could think that, all right, let's try L'Hopital's rule, and here's where the problem comes in. The derivative of 5t plus cosine t is t minus sine t, not t, 5 minus sine t, and the derivative of 2t is 2. And this does not exist because the numerator is going to be bounded between 4 and 6, sine being bounded between -1 and 1, so 5 minus 1 is 4, 5 minus -1 is 6, and it's bounded between there. The denominator is constant, and so I'm going to keep on oscillating from 4 over 2, which is 2, to 6 over 2, which is 3, so it's going to be, oscillating. It's never going to settle down. But if you recall, whenever I talked about L'Hopital's rule, there's always the requirement that this limit existed. If it does not exist, it doesn't mean that this can't exist. So if we were smarter, instead of jumping right into L'Hopital's rule, I'm going to rewrite the limit. T approaches infinity. I'll split the numerator. 5t over 2t plus cosine t over 2t. And now we can see this portion here is 5/2, and this portion here approaches 0 because cosine is bounded from -1 to 1. It's a relatively small number in the swing of things, but the denominator is going towards infinity, so I have a bounded value divided by something that's becoming infinite. And so since my limit is 5/2, it's a number that's not 0, not infinity. That means that f and g grow at the same rate. Of course, f might be a little bit steeper, but their growth rates are the same. They both grow linearly. All right, now looking in some of the big use of this. So this is actually an incredibly important idea in computation because I want to have, when I'm doing computing, functions or operations that grow linearly or polynomially. I don't want them to grow exceedingly fast. So I want to try to get these to grow as slowly as possible. And this notation is how we notate that. So for big O, this notation means the following. If f of x is big O of g of x, then that means that either f and g grow at the same rate, or f grows slower. Okay? Little o notation is very similar. F of x equals little o of g of x, except in this means that f strictly grows slower. Big O is something I see much more often. It's like a less than or equal to. Little o is a strict less than. So let's see some examples of this. If I want to show that natural log of x is little o of root x, what I can do is this. So I will start off by the same thing, doing the growth rates, x approaching infinity, of natural log of x divided by root x. Now in here I want to show that this natural log grows slower than that, root x, so I want this limit to equal 0. And we can see that as we approach infinity, the numerator approaches infinity, the denominator approaches infinity, so I can use L'Hopital's rule, and it will work for this one. So limit as x approaches infinity of the derivative of the natural log of x is 1 over x. The derivative of root x is 1 over 2 root x. If we are not smart about this, I can just try to go on, and when I put infinity in here, I will get 0. It's approaching 0. When I approach infinity for x, this approaches 0, and I might try to keep doing the derivatives. But let's clean this up. If I clean up this doing some algebra, I'll actually be able to evaluate the limit and kick out of this early. So that's equal to the limit as x approaches infinity. 1 over x means that I'll have an x in the denominator, and divided by 1 over 2 root x, I can flip it around and multiply by the reciprocal and get a 2 root x in the numerator. Now, again, if I just put in infinity, not thinking, I would end up with infinity over infinity, and actually if I did L'Hopital's rule here, it'd work out, but there's a smarter thing I can do, and that's the following. I can do root x divided by x, and what I get is, still this limit, 2 over root x. Let me explain that. So, because x over root x is equal to x to the first over x to the 1/2, which means I subtract the exponents and I get x to the negative 1/2. Negative means it's going to go to the denominator. 1/2 means I have the square root. Now, the numerator is approaching 2. It is 2. The denominator is approaching infinity, and I see that this limit is 0. That means that natural log of x grows slower, strictly slower, and therefore the natural log of x is little o of root x. Natural log actually grows incredibly slowly. It goes towards infinity, but grows very slowly still. All right, one more example. I want to show that root 10x plus 3 is big O of root 3x minus 2. So I'll start off, do the limit as x approaches infinity of root 10x plus 3 over root 3x minus 2. And I can see if I just put in the infinity or approach infinity, the numerator and denominator both approach infinity. But if I just start taking derivatives, I'm going to get stuck in a really, really ugly loop where I'm going to end up still having these radicals and some other numbers to boot. So that's not the best option here. The best option is to do a little bit of algebra on this and rewrite it as the limit as x approaches infinity of the square root of 10x plus 3 divided by 3x minus 2. If I consider what's happening inside the square root, so limit as x approaches infinity of 10x plus 3 over 3x minus 2, these approach infinity over infinity. So I can do the derivatives, L'Hopital's rule, and get the limit as x approaches infinity of 10 over 3, which is, of course, 10/3. And that lets me know that this limit up here will equal the square root of 10/3. This all implies that root 10x plus 3 grows at the same rate as root 3x minus 2, and therefore root 10x plus 3 is big O of root 3x minus 2. Now, this problem here, not so much this problem here, but this problem here is a little silly. Usually we want the simplest form of this. So this is a square root function. Usually I would do, or almost always, useful math, I would have something simple in here because all of these radicals sort of grow the same way. Root 3x minus 2 grows at the same rate as root x. And that tells me the most. But still, this is the mathematical way to evaluate this. I hope that helped out. Please comment below with any questions.